Good afternoon, geometry students. I hope that you are doing great. I'm looking forward to seeing you soon. I'm doing these videos before our classes actually start just because I want to have them ready for you in advance so that we can all be prepared together. So anyway, I'm excited about teaching you another lesson. We have done notes for Chapter 7 and Chapter 8. We're going to start our first notes on Chapter 9 today, Section 9.1. And we're going to be doing lesson 9.1 on Pythagorean theorem. So we did already learn about Pythagorean theorem at the beginning of the school year, so last quarter. But we're going to do a review of Pythagorean theorem and then also talk about the Pythagorean theorem. You might call it the converse. And so we'll kind of go from there. So let's write down on our notes first what the Pythagorean theorem is. So I think in this particular case, normally we write a squared plus b squared equals c squared. But for this lesson in particular, it can be a little bit less confusing if we write it this way. So Pythagorean theorem tells us that if we have a right triangle, then c squared is equal to a squared plus b squared. So if a triangle is a right triangle, c squared is equal to a squared plus b squared. What's interesting is that the converse is also true. So the converse would be if c squared equals a squared plus b squared, then the triangle is a right triangle. So we can read that theorem either direction. The interesting thing is, even if the converse isn't true, we still know something about the triangle. So let's look at two other possibilities. So other possibilities. Something else that can come up is we can get c squared and have it be less than a squared plus b squared. If c squared is less than a squared plus b squared, then the triangle is acute. And the last possibility, because c squared is either going to be equal to that, less than that, the other possibility is if c squared is greater than a squared plus b squared, then the triangle is obtuse. So that is in essence what this lesson is about. We'll talk about a few other kind of little things as we go through the notes. The other thing that we're going to talk about is something called a Pythagorean triple. A Pythagorean triple is three integers, so three numbers that are not fractions or decimals, such that a squared plus b squared equals c squared. And then we want to see whether or not, what can happen is that anytime you end up with, let's do an example of a Pythagorean triple. Pythagorean triple. A common Pythagorean triple is 3, 4, 5. Basically, if we take any multiple of that, so if we multiply it times 2 and got 6, 8, and 10, that would also be a Pythagorean triple. Again, what I mean by that is three numbers that are integers where c squared does equal a squared plus b squared. Okay, so let's do some examples, and then we will obviously in class go over more homework problems to kind of nail this down further. So example number 1, find the value of x and then tell whether the side lengths form a Pythagorean triple. So we'll draw a right triangle, and then we will label two of the sides 5 and 12, those are the legs. If we do Pythag, we would say, okay, c squared is equal to a squared plus b squared. So x squared would have to be 25 plus 144, or 169. Then when we take the square root of both sides, we get that x is 13. So using the Pythagorean theorem, we can see that the third side, the hypotenuse, has length 13. This is a Pythagorean triple because we have three numbers that work with Pythag, And those numbers are integers. In other words, they are not decimals or fractions or square roots. Okay, let's go ahead and look at problem number 2. Again, we're trying to see if there is a Pythagorean triple here. We're going to put an x here and a 7 there and a 25 there. By the way, on this last triangle, we would call this a 5, 12, 13. This is a very common Pythagorean triple, and it would be a good one for you to memorize. Let's do Pythag on example 2. We want to set 25 squared equal to x squared plus 7 squared. Notice that we always have our c be the hypotenuse, the longest side. So if Pythagorean theorem is going to work, you have to pick the longest side for c. So 625 is equal to x squared plus 49. I would subtract 49 from each side and get 576 equals x squared. And then, of course, I would take the square root and get that x is 24. This is another common Pythagorean triple. This would be a 7, 24, 25 Pythagorean triple. This is not as common as the 5, 12, 13 or the 3, 4, 5, but it still does come up a fair amount. Okay, let's do the third example here. We have a right triangle with side lengths of 6 and 10 and a hypotenuse of x. When we do Pythag in this case, we get that x squared is 136. Now, I do want to remind you what we need to do anytime we're simplifying a radical. We do need to look for pairs. So we're going to do a factor tree and see that 2 goes in 68 times, 2 goes in 34 times, and 2 goes in 17 times. So when I take the square root here, instead of saying the square root of 136, I'm going to say the square root of 2 times 2 times 2 times 17. Because there is a pair of 2's here, I can take that pair out, and this becomes x equals 2 times the square root of 34. Now notice this is not an integer. This is an irrational number. That means if we put it in decimal form, it would continue on indefinitely. So this is not a Pythagorean triple. In order for something to be a Pythagorean triple, you need all 3 sides to be integers. So you can think of it as whole numbers if you would like. All right, now we're just going to do a couple versions of the converse, and then a couple others after that as well. So again, feel free to pause the video as you need to copy down problems or notes or take a break. For example number 4, it says verify that the side lengths form a triangle. Is the triangle right, acute, or obtuse? Now, in order for the side lengths to form a triangle, we talked about this earlier, it needs to be that the 2 smaller numbers are greater than the third when you add them up. So let's do example number 4. If my side lengths are 20, 40, and 30, if I wanted to verify if this could be a triangle, I would have to take the 2 smaller sides, 20 and 30, add them up to make 50 and see if that's more than 40. Because it is true, when I add up the 2 smaller sides, that I get a number bigger than the third. These 3 sides could be the sides of a triangle. Now, to see what kind of triangle I have, I square the biggest one, put it on its own on the left, and I square the other 2 and put them on the right. So I would have 1600 is equal to 400 plus 900. And this is like what I'm asking myself. Is this true? Well, when we do this, we can see that 1600 is actually bigger than 1300. So since 1600 is bigger than 1300, this would be an obtuse triangle. Okay, let's look at example number 5. The numbers here are 7, 6, and 5. These could represent the side lengths of a triangle, because if I add up the two smaller ones, 5 and 6, I get 11, which is bigger than 7. Now, what I can do is do the converse of Pythagorean theorem to see if I have a right triangle or not. So I want to see, is 49 equal to 36 plus 25? When I add 36 plus 25, I get 61. 49 is actually less than 61. So this triangle would be acute because c squared, the largest side squared, is less than the sum of the other two. Okay, so let's go ahead and do one more example kind of like this, and then we'll do one different example and we'll be done. So for example number 6, we've got a triangle here that we can see because the two side lengths are the same here. We call that an isosceles triangle. And we don't know the altitude or the height, but the base is 18. The thing that's important for us to understand is that these two triangles are going to end up being congruent. And because of that, this piece right here is going to be 9, and this piece over here is going to be 9. So there are a variety of reasons that we can say that is true, one of which is the hypotenuse leg theorem, because each of these triangles share the same leg and same length hypotenuse. All right, now that I know that that base, this half of the base is 9, I can do Pythag for either of the two right triangles there and see what x is. So 26 is the hypotenuse, and then I would need to set that equal to 9 squared plus x squared. When I square 26, I get 676. 91 squared is 81. When I subtract that, I get 595. When I do a factor tree for 595, I can see that 5 goes in 119 times, and then 7 goes in 17 times, but there are no pairs. So even though it's a very large number, the answer is just square root of 595. So that would be how we would find x in that situation. All right, we're going to do one last example here. Example number 7. We're going to find the area of the isosceles triangle. So let's do example 7. We have an isosceles triangle. We're given that these two sides here are congruent. They're both 50. And then this length right here is 14. So in this particular case, we would label that as x, and then that would be our height, and we would just do Pythag for the right triangle. Remember, Pythagorean theorem is only valid for right triangles. So when we did Pythag here, we would have x squared plus 14 squared equals 50 squared. When we square 14, we get 196. And when we square 50, we get 2,500. Now, when I subtract 196 from each side, I'm going to get x squared equals 2,304. If I take the square root of that on my calculator, it actually ends up being 48. We could do a bunch of pairs in there, but it just ends up being 48. So now that I know the height here is 48, I have to remember that area is 1/2 the base times the height of the whole triangle. So if this portion of the base is 14, this portion is going to be 14. The whole base will be 14 plus 14, or 28. And then the height, as we just said, is 48. Half of 28 is 14. 14 times 48 is 672. So the area of this triangle will be 672 units squared, whether that's feet squared, yards squared or whatever. Okay, I know this was kind of long. Thanks for hanging in there and have a great day.